Good afternoon, everyone. Um, do let me know, as always, if the sound and video and everything is coming out across okay. I do apologize. I realized that the reminder email that was sent out on Monday had the wrong link to it. So hopefully everyone was able to find the proper Part 2 live stream and not the Part 1 live stream. If you're watching this after the fact because you accidentally went to the wrong page, my sincere apologies. I have made sure to update all of the other reminders, dig the last reminder so it won't happen again. Hey JD, all right, great, good to hear that sound is good. All right, let's just jump right into it because there's an infinite number of things to talk about. I'll briefly review what we talked about last week, just the first few sections of the chapter. If there are any questions about anything that we covered, again, don't hesitate to ask a question here in the comments if you're watching live, or on the Patreon comments if you're watching after the fact. So discrete choice is all about modeling how individual entities make choices. I will refer to these entities as agents. The term here really carefully denoting the assumption that these individuals have some notion of agency. They're actively making these choices. What are they choosing? Well, they're choosing from a finite choice set. This is where the discrete part comes in, right? They're not choosing some continuous value. They're not choosing from a spectrum. They're choosing from one of a finite number of possibilities. Those possibilities are referred to as alternatives, and the collection of alternatives is known as the choice set. If there are multiple choice sets, if you have multiple individuals making multiple decisions across different collections of alternatives, then I'll often refer to those as choice subsets, just to try to be as clear as possible, right? Because this is one of these weird things where you have a set, and then you have a subset. People often refer to the subset as a set itself, and it can kind of become unclear whether or not sets are mutually exclusive, whether they can overlap, and things like that. Now, the way we model these decision-making processes of these individual agents is by assuming that there is some latent utility that each of these agents allocates to each of the alternatives within a particular choice subset. If we knew those utilities exactly, then choices would be deterministic. It would just be, by construction, the alternative that has the highest utility. More realistically, we won't know what these utilities are, either because they're uncertain or because they're variable. Whether the kind of variability is capturing kind of temporal variability or just inconsistency in how people make decisions, doesn't really matter. It all gets modeled with a probability distribution. So we have a behavioral model which allocates probability to all of these different utility configurations. Now, when we have a probabilistic utility model instead of a deterministic utility model, decisions no longer become obvious, they become probabilistic. And the way we calculate the probability of each possible choice is by summing up the probability allocated to these subsets of utility configurations, where one utility is larger than all of the others, and that gives us these choice probabilities. So in the actual implementation of a discrete choice model, what we're really doing is we're deriving choice probabilities from the underlying behavioral model, this probabilistic utility model, and then everything just becomes a categorical or a multinomial model. One of the common frustrations I have with a lot of discrete choice literature is that a lot of the descriptions, the nomenclature, terminology is really focused on the end product in all of this. In particular, the form of the choice probabilities, rather than the assumptions that lead to those choice probabilities. So the classic example, which we'll see in a second, is the so-called logit model, which is named after the form of the choice probabilities and not the probabilistic utility model that we have to assume in order to derive that particular logit style probability. So I take a slightly different approach here in my nomenclature, really trying to emphasize the structure of the assumed behavioral model, and then deriving everything from there. I think this is also what really differentiates discrete choice modeling from just arbitrary modeling of discrete outcomes. It's not the final observational model, it's how we derive the probabilities in that observational model. Now, one of the kind of key points of interest in a discrete choice modeling application are what are often referred to as substitution patterns. Right? The idea is what would happen, or what does happen, if alternatives are added or removed from a choice set. So another way of thinking about this is we have all these alternatives. We can form one choice subset from a subset of those alternatives. And we can form another choice subset from another subset of those alternatives. And the question is, how do choice probabilities change when we move from one choice subset to another? Now, they're always going to change in absolute terms, because if we add or remove an item, that's going to change the normalization, it's going to change the choice probabilities. But things like ratios of choice probabilities, relative choice probabilities, these things can be much more stable. And the question is, how stable are they? More generally, substitution patterns really concern which alternatives make good substitutes for one another. If we have two alternatives that are good substitutes for each other, then removing one will just funnel all of that probability to the remaining alternative, because it's just as good as the one that we removed, or it's just as good relative to any of the other alternatives which are different or distinct in some way. Similarly, if you add an alternative that is a good substitute for an existing alternative, then it's much more likely that that new alternative is going to get its probability from its substitute that already existed, rather than any of the other alternatives that existed, because those are less good substitutes. So that's kind of the general qualitative notion of substitution patterns. But in practice, substitution patterns are often presented in terms of ratios of choice probabilities, and this particular question of whether or not all ratios of choice probabilities are invariant to changes in the alternatives. This is known as independence from irrelevant alternatives, and it's somewhat awkward in the sense that this is the canonical substitution pattern, but it's often the least desired substitution pattern. This is the substitution pattern that's easiest to work with mathematically. It's the most rigid, in the sense that if you make this assumption, it's relatively straightforward to derive new choice probabilities from existing choice probabilities without having to go to a whole new probabilistic utility model underneath. And it's also the substitution pattern that we get from the simplest discrete choice model, the kind of classic introductory discrete choice model that we'll talk about in just a second. However, in a lot of applications, we don't want that behavior. If there are alternatives that make better substitutions for each other than others, then this IIA behavior is not really going to be appropriate. It's going to poorly capture the substitution patterns. And that means when you try to learn from observations in some set of choice subsets, and then try to generalize to new choice subsets, that generalized prediction, those inferences, aren't going to perform very well. So a lot of the kind of formal quantitative discussion of substitution patterns is all about IIA. But in practice, what's really more interesting are these more qualitative substitution patterns. And they're just kind of harder to try to quantify, at least before looking at particular data and seeing what happens with particular observations and inferences. All right, now the model that we started talking about, or the kind of classic initial model that is presented first in every discrete choice presentation, and indeed here, is what I refer to as the independent Gumbel model. And in the independent Gumbel model, we assume that the probabilistic utility model decomposes into a component model. So it's a product of component models for each individual utility. And then for that component model, we'll assume a Gumbel. Gumbel can be motivated from this extreme value perspective, but in some sense, its real power, its real motivation is that it's mathematically straightforward to work with. So we can derive choice probabilities in closed form, which is pretty unique amongst lots of models that we might consider, but in particular across to the extreme choice world. It's kind of the exceptional extreme choice model that admits these kinds of explicit calculations. And so if you go through those calculations, what we get is a form like this. These choice probabilities can be written as softmax functions. The softmax function is also known as a multi-logit function, which is often shorthanded just a logit function. And that's why this model is often referred to as a logit model. Again, I don't like that terminology because it's focused on the outcome and not the assumptions that we made to derive that outcome. The independent Gumbel model has all kinds of redundancies built into it, so we have to do some careful kind of translation to relative parameters, relative baseline utilities, relative scales, in order to avoid those ambiguities in practice. That will ensure that we get nice, well-behaved inferences. It also gives us a much cleaner interpretation for all of our parameters. Baseline utilities on their own are kind of abstract because they're really only well-defined relative to the other baseline utilities. And moving from the absolute baseline utilities to these relative baseline utilities makes that a little bit more explicit. So things like building prior models, much more straightforward when we're working with these relative parameters rather than their initial absolute parameters. And then the big thing to look out for is that when you move to these relative parameterizations that avoid these redundancies, they are different parameters. They do have that slightly different interpretation. A lot of presentations of discrete choice modeling do not make this explicit. They use the same variables for the absolute and relative behaviors. You'll see a lot of recommendations to just set certain things to 0 and cross your fingers, which I obviously am not a big fan of. So I'm being very explicit here and using different variable symbols to denote all of these different parameters. And you'll see by the end we basically exhaust the entire Greek alphabet, but I think it's worthwhile to make sure that we don't have any ambiguity about what's happening in any given circumstance. As I hinted at earlier, this independent Gumbel model exhibits IIA. It's one of the reasons why it's kind of the classic substitution pattern. But that's all pretty abstract. So now we can pick up to where we ended and get into the demonstration. So now we're going to take all of these abstract ideas and see how they manifest in a real explicit analysis. Well, at least a analysis of simulated data. So we're going to assume 6 agents, 9 alternatives, so a single fixed choice set, and 1,000 observations. Note that this means that agents will be making multiple decisions. And this is, while nice in a lot of applications, a little bit unrealistic. In most, especially kind of marketing applications, you're dealing with a consumer making a decision once, if at all. If they're, in the rare circumstances where they are making multiple decisions, it's usually some kind of, more of kind of a temporal thing, where their underlying utilities are changing across time. So it's not this just perfect replication. I'm doing this just to make the posterior inferences as unambiguous as possible. Not that this is realistic by any means. In particular, all these replicated observations across a small set of agents is I would say the most unrealistic part of this. And one of the consequences of that is that these sigmas, these relative agent scales, are often much harder to infer in practice than what we'll see here. We're not going to get great inferences of them anyways, even with this kind of surfeit of observations. But keep in mind, it gets even worse in practice. And so it's one of these weird things to look out for. These scales are kind of always there, but they're even once we avoid the explicit redundancies, or the full redundancies, they're just pretty degenerate given the amount of data they need to pin down. All right, so the first thing we're going to do is simulate some data. So we'll simulate some absolute baseline utilities. We'll simulate some absolute agent scales. From those, we can derive choice probabilities. Again, we're just using the softmax. And Stan has this naming convention where when it transforms the input, it doesn't actually use the name of that transformation. It uses the name of the inverse transformation. This is an old statistics notation that I am very much not a fan of, but it's pretty prevalent. And in the case of the categorical model, where it's applying really this multi-logit function and not the one-dimensional logit function, you'll see the kind of shorthand here as well. So it's not categorical multi-logit, it's categorical logit. Why? Because everyone hates you and wants you to be confused. Simulating data from the model is relatively straightforward, and that allows us to start thinking about visualizations. So the tricky thing with discrete data is there's really not that much you can do with it, right? You can look at each response individually, but otherwise, all we can really do are look at histograms. So we can look at histograms over all of the data. We can also split those histograms up, stratify them across agents. Right? In this case, this is really the only notion of heterogeneity that we have available to us. Although you can see some interesting patterns, right? So there's some common behaviors. Agent alternative 5 seems to be pretty common across all agents, but there are some differences. Right, agent 3 seems to have very high frequency at that popular alternative, whereas agent 1 seems to have even more frequency at agent alternative 9. So alternative 5 is still pretty up there, but alternative 9 is now a little bit higher. Agent 6 similarly. So we're seeing different patterns across the agents. And so we want to be able to understand not just the behavior of these alternatives and the appeal of these alternatives, but also the behavior of the individual agents that are making these choices. If we can't account for that, then trying to generalize to other agents is going to be very difficult. So the first thing we'll do is not take any of these redundancies into account and try to implement this model in a naive way. So we'll model the absolute baseline utilities, we'll model the absolute scales, and see what happens. The model itself is straightforward to implement. We can calculate the log choice probabilities with a softmax application, and then we can just plug that into our model. Now here I'm doing a little bit of shorthand. When you call something like categorical PMF in Stan, all it's doing is it's looking up the component that was chosen by the data you plugged in, and then returning the log probability for that component. So here I'm just doing it directly. If the choice M was the observed choice in the mth observation, then we want to look at that choice probability for the nth agent, and then allocate the log of that to the overall model accumulation. Running that through Stan, no problems with HMC. This is a pretty well-behaved model. Or mathematically, it looks relatively straightforward. But if we start looking at our inferences, we start knowing problems, or we start seeing problems. Look at the posterior uncertainties of the baseline utilities. Plus minus 200, right? These are huge ranges, especially when these numbers get plugged into an exponential. Right, so softmax is just exponentiating things and then taking ratios. You plug a 200 into an exponential, bad things happen. So that's already a sign that something's a little bit amiss. And then the boundary here is the scope of the prior. So this is the prior keeping us within plus minus 200 or so. If we didn't have the prior, you would imagine that this posterior would go even further, right? And this is that degeneracy manifesting. Same problem with the agent scales. These are also pushing up against the containment of the prior and have really, really wide ranges. So that's just to demonstrate that these redundancies are in fact real. They're not made up. We can see them, and we can immediately see why they're going to be problematic. So to avoid those redundancies, we need to anchor an individual agent and an individual alternative, and then define relative agent scales and relative baseline utilities with respect to those anchors. Now, in theory, it doesn't really matter which anchor you choose, but in practice, it's often a good idea to choose an anchor that has a lot of observations. The more the anchor entity has been observed, the kind of more well-behaved your marginal posteriors will be. Right? You're comparing things to a very clear baseline. If you're comparing things to a very uncertain baseline, that uncertainty will propagate into your marginal inferences. The actual joint inferences don't change that much. The relative behaviors are all pinned down as well as they're going to be. But when you start looking at individual marginal inferences, it's just a little bit cleaner. So here we'll take the agent with the most observations and the alternative with the most observations. And that will define our anchor. So in this case, it's agent 1. And then for the alternatives, it'll be it'll be alternative 5. Now I'll use this add anchor function here. This just, it takes a vector of j minus 1 elements, and it inserts a 0 at the appropriate place, right? So 0 is going to be the relative baseline utility for the anchor alternative. And we should do a little bit of care here because to distinguish when it needs to be inserted at the beginning, at the end, or somewhere in the middle. And then because we're anchoring the first agent, that's a little bit easier. We can just append that to the beginning without any ambiguity. But if we wanted to be a little more flexible and anchor an arbitrary agent, we could just use the same add anchor function that we did here. Right, just kind of showing you two different approaches to this. And otherwise, other than fixing that scale to 0, the model's the same. Now, we do want to be careful with the prior model, right? When we go from absolute behaviors to relative behaviors, the prior model should change. So here, because we're simulating data, it doesn't really correspond to any real model. I'm not going to try to translate it. I'm just going to kind of come up with a new prior model. If you did try to translate it, you'd get something real wacky. You get because you're trying to take into account both the relative, the alternative anchor and the scale anchor. You end up having to deal with the division of two normals, and that gives you something with like it's like a Bessel density. It doesn't have a nice clean name. It's not a very well-known density, but it's a mess, and it's very, very expensive to evaluate. So while you could work with that, it's much easier just to reason about the relative behaviors directly. So give that a try. No problem with the computation. And now our inferences are much, much more strongly informed. Right, so not only do they look relatively narrow in of themselves, they're small numbers and they're much closer to 1. You can see that they're concentrating far, far within the scope of the prior model. So now the prior model is not really doing all that much work. It's the likelihood function that's really dominating the structure of the posterior, and it's because we eliminated the redundancy in that likelihood function. Now, in this case, we know the model is correct because we simulated the data, but just to kind of get our feet wet, we can think about what a good retrodictive check might look like. And in this case, we have all of those histograms. So we can compare the observed histogram to posterior predictive histograms, and they look nice and very much in agreement here. We can look at the behaviors across individual agents. Still looks very good. You'll notice there's more kind of heterogeneity here. In the agreement, but it's all pretty consistent. So even look at something like Agent 1, where there's not a perfect overlap, we always want to keep in mind we're looking at lots of different things, and we're going to expect there to be some variability in the agreement. And also these quantile intervals are only capturing 80% of the posterior predictive distribution. So there's tails here that we're not visualizing, just because they're kind of too computationally tricky to estimate. And then we can look at our inferred parameters to the true parameter configuration that we simulated the data from. And everything here matches really well. So we have our the true relative baseline utilities, the true relative scales, and we're pinning things down quite well. Now, the relative baseline utilities, those get informed pretty well, given over across all these observations. But the agent scales, note that these are much less strongly informed. So this is a thing we're going to see over and over again. Even when we have a preponderance of observations that's not super realistic to a lot of applications, these agent scales do not get informed very well. However, if we don't take these scales into account, then we're not going to propagate the right uncertainty, the right heterogeneity into predictions for new agents, and that will lead to overconfident predictive distributions and inferences. So I always want to keep that in mind. Now, one thing about multiple observations over a fixed choice set is that we can simplify the observational model, the evaluation of the observational model, quite dramatically. The choice probabilities for the fixed choice set and a single individual agent are always the same, right? There's no need to recalculate those every single time. So one way of making that a little bit more manifest is calculating the choice probabilities once, and then aggregating all of the observations for a particular agent choice set pairing. And then we can turn all of those categorical evaluations into a single multinomial evaluation. And that's what I've done here. So we aggregate all of the observations for each agent into aggregated counts, and then we use those aggregated counts in a multinomial model, using the same log choice probabilities. And this just makes it a little bit more explicit that we only need these choice probabilities once. This is mathematically the same model. Let me note this little thing here. All right, what are we in? Section... so we see a stray Z-hat warning. This is not really of concern. Z-hat warnings, just to remind you, they really kind of indicate heavier tails. So if we're looking at posterior means of tau free 5, that might be problematic. But we're not typically doing that, so we don't have to worry about that here. I guess one thing I will note is that a heavy tail for the relative taus, the relative scales, not actually that surprising, because the relative scales come from dividing two normals. And dividing two normals, even though the numerator and denominator are relatively well behaved, the ratio can be pretty dispersed and exhibit very, very heavy tails. So we want to be careful with that. All right, so now we can go through our usual progression, look at our retrodictive behavior. Everything looks good, both aggregate and then for individual agents. Again, it's the same model. So if you look at these retrodictive behaviors to the previous retrodictive behaviors, they're going to look absolutely similar. The only thing we have to be careful about here is that because we are predicting aggregate counts and not individual counts, we can't use the plot his quantiles function anymore. Instead, we have to transition over to using these discrete push forward quantiles, because we've already calculated the bin contents, and now we just want to visualize the bin contents directly, as opposed to the his quantile function, which bins everything and then plots them. One advantage of that is this is much faster, because we've already done the binning. And then we can verify that we recover the parameters well, which we do. Any questions so far about the basic implementation of the independent Gumbel model? Okay. I do want to be cognizant that there is a pretty long delay here, so I take these awkward pauses to make sure I catch any questions. So if you want to now consider the heart of discrete choice modeling, which are the question of substitution patterns, we need more than one choice set. So here we're going to consider observations across 3 choice subsets. There's a nominal choice subset that includes 9 alternatives. There is a second choice subset that includes only 8, right? So it's given by taking the first choice subset and removing one of those elements, one of those alternatives. And then there's a third choice subset, which is given by adding an alternative to the first choice subset, filling out all of the possible alternatives. Right, and I added a figure here to visualize those possibilities. So the main thing about these choice subsets is that is the relation to each other. We get the second choice subset by removing an element from the first. We get the third by adding an element, adding an alternative to the first. And so by looking at the choice probabilities between subset 1 and subset 2, and choice probabilities between subset 1 and subset 3, we can start getting a handle for what happens when we add an alternative versus removing an alternative, right? And focus on those particular substitution patterns. Now, implementation-wise, there's a few things that we have to consider here. The first is that how do we consistently index the alternatives in each of these choice subsets? Because they have a different number of alternatives, we can't use the same indexing in all 3, right? The local indexing in each stand program has to, for example, for choice subset 2, would be 1 through 8. We can't have a missing element there. So there's going to be a difference between the local indexing and the global indexing. And that's what this function here does. So we'll just want to make sure that we translate things back and forth appropriately. The other thing that we have to worry about is that because there's a different number of alternatives in each choice subset, when we try to aggregate all this data together, we're going to end up with ragged arrays, right? The aggregated counts for each agent across these different choice subsets are not going to be the same size. So to programmatically run through everything, we're going to need to combine all these individual these ragged components into one monolithic array. And this is something I've done in a lot of case studies and various chapters so far. But here's just a nice figure to kind of really clarify what this code does. So we have 3 arrays here of different sizes. We can't stack them into a rectangular structure because they don't have the same length. But we can stack them into a single long one-dimensional array and then use the start and end indices to pull out the individual arrays as needed. So there's no constraint on the start and end. And that allows us to have different sizes for each of these component arrays. Now I'm also going to up the... yeah, so ragged arrays are kind of a mess. I can't speak for stand development these days. There's a lot of just weird decisions that are made. Ragged arrays come up a lot, and they've always come up a lot. This has kind of been a known thing. For whatever reason, it hasn't been supported. The way ragged arrays are handled in a lot of programming languages is not super efficient. Because it's basically just creating all these 3 separate arrays and then having addresses to them where they're not contiguous in memory. Something like this, the B figure here, is how you would do it efficiently, but it's not always done this way. And I think the main problem is that this kind of memory efficient approach requires you to have 2 bits of information. You need to know the starting address and the length, or the starting address and the ending address. And for whatever reason, those kind of get awkward to deal with, so people rather prefer having just the one index and then having length kind of be internal to the array structure in some sense. So, you know, like in Python, the length of the array is part of the array itself. There's lots of ways of trying to approach it and trying to implement in practice. I don't know why it hasn't. But once you kind of get in the habit of doing this, it's really not that difficult, right? The hardest part is just constructing the start and end indices. And honestly, like once you have a function like this, you can just wrap it in a little package and reuse it over and over again. I guess that is one thing that does complicate the implementation of a function like this in Stan, is the translation to what kind of data structures in R and Python you would be passing in. And then how does that convert it, and how does that get converted back? So things like this. So one thing that doing it yourself forces you to do is work with the same data structure in R and Python that you're using internal to Stan. So it's a little bit more uniform, right? It'll cost you have to do it yourself. But hopefully this figure helps clarify what's going on and the code doesn't seem as mysterious. And the other thing I'm going to do here is I'm going to amp up the number of observations quite a bit. This many observations for this few agents, not the most realistic, but I don't want there to be much ambiguity in the inferred substitution patterns. I want those to be as clear as possible. So what does our Stan program look like overall? So we pass in the number of subset configurations, the total number of alternatives across all those configurations, so the length of this concatenated array, and then all of the beginnings and ends. Alts tells us the global indexing of those local elements, and that's what allows us to translate things appropriately. This is just for the simulating the data. So for each observation, we choose a subset. Given that subset, we look up what the alternatives in that subset are. Once we know what the alternatives are, we can look up their baseline utilities, and then compute the choice probabilities and simulate an observation. So now when we're looking at the simulated data, there's a little bit more stratification available, right? We can not just look at, well, I guess we have to stratify because we don't really know how to pool observations across different choice subsets, right? For one, the indexing is off, and for another, it doesn't really make sense to compare frequencies across things with different possibilities. Right? The way that you would reconcile those different behaviors is by establishing a substitution pattern. Right? That translation is exactly what a substitution pattern is. So all we can really do here is look at the aggregate counts for all of the agents across the 3 separate choice subsets, keeping in mind that these are local indices. So the alternative 5 here doesn't necessarily correspond to alternative 5 in choice subset 2, or choice subset 3. These could be arbitrarily permuted, right? So it's not just a question of like you remove an element and then the indices go down by 1. In theory, these labels could be all over the place, and that could just be due to arbitrary, organization and manipulation of the data, or it could actually be intentional. If you imagine something like a double-blind study, where the alternatives have been given arbitrary labels by the analyzer and people who collected the data. And so we have to translate between those to make sure that everything is consistent. All right, so the first thing we're going to do is we're going to fit the data from each of the 3 choice subsets separately. We're going to use the same model that we used before, and we just have to separate out the data for each of those possibilities. Now, the immediate complication here is how do we ensure that the relative baseline utilities and those 3 fits are consistent with each other. They're comparable with each other. To do that, we have to choose the same anchor across the 3 models. The choice probabilities will be comparable. But if we don't make the anchor consistent across the 3 fits, then the omegas will not be directly comparable. So this requires two things. So it requires one thing, and then there's an additional ideal constraint we would like to have, but isn't strictly necessary. The one absolute requirement is that if we want a consistent anchor, it has to be an alternative that shows up in all three choice subsets. This isn't necessarily possible. If you have lots of different choice subsets, there might not be an anchor that appears in all of them. The ideal on top of that is if there are multiple alternatives that appear in every choice subset, then we would choose the one that is the most prominent. So in this case, we'll look at all of the alternatives that are common to all the choice subsets. So you'll notice that 5 doesn't show up here, and 8 doesn't show up here. So it's 1, 2, 3, 4, 6, 7, 9, and 10. These are the common alternatives across all the choice subsets. And then of these, alternative 9 is the most common, the most chosen. So we'll choose that as our anchor. And then lastly, to make sure, this is alternative 9, that's our global indexing. Right? We need to translate that to the local indexing in each choice subset if we want to be able to anchor things consistently. So I would make sure that we'll translate back to those local indexes. Now we can run our independent gamma model in a loop over all of those choice subsets. And we see there's no computational problems, as expected. And now we have 3 different posteriors over 3 different sets of data that we can use to see if we get consistent results. So the first thing I'm going to do here is I'm going to take the log choice probabilities that were saved in the stand program and exponentiate them, just so that we have absolute probabilities. And then we're going to look at agent 5, alternative 3, and alternative 10. Get a global indexing for 3 and 10. That will then translate back to the local indexing to get the right parameters. All right, sorry. So we already did that, right? So, yeah, here we go. So the agent 5, global index, alternative indices 3 and 10. When we go to pick the choice probabilities up calculated from each of those fits, we want to we'll need to translate back to the local indices, get the corresponding log probability, and then exponentiate it. So when we look at J1 probs here and J2 probs, these have already been translated back into global indices, so we have proper comparisons. So alternative 3 and 10 and choice subset 1, they look reasonable. They're both pretty small probabilities. So notice the scale here. This is down below 10%. There's no reason why they should have similar values, but in this case they happen to. And there's really not much more we can say. We look at just the one choice subset. But now what happens when we go to choice subset 2? So both of the choice probabilities change. But the choice probability for alternative 3 changes much more. Why is that? So remember, we go to choice subset 1, choice subset 2, we remove an alternative. And in this case, it looks like the alternative that we removed was a good substitute for alternative 3, or it's a better substitute for alternative 3 than alternative 10. So when we remove that alternative, we have excess choice probability. It has to be reallocated somewhere. And because 3 is a better substitute for the removed alternative than 10, more of that excess choice probability is going to move to alternative 3 and alternative 10. So while they both increase, the choice probability of alternative 3 increases more right? And again, that's a manifestation of the substitution pattern. Wait, sorry. Okay, hold on. I'm jumping the gun a little bit. So we don't necessarily know what a good what the substitution patterns are here. We don't know if there are heterogeneous substitutabilities, if you will. So all we can really say here is that both choice probabilities increase, right? That's all we should be able to say here. Now, when we go from choice subset 1 to choice subset 3, we are adding an alternative. A new alternative requires choice probability. The choice probability has to be taken from the existing choices, and indeed, the choice probabilities both decrease when we move from choice subset 1 to choice subset 3. Right? So the increases and decreases, those are making sense. The question, however, that is really of interest when we talk about substitution patterns are the ratio of choice probabilities, right? This is what denotes whether or not different alternatives are better substitutes for each other than other alternatives. And so to do that, we're going to look at ratios of Q choice probability 3 to choice probability 10. Again, for the fifth agent, just taken arbitrarily. So now we can compute that ratio of choice probabilities across all three choice subsets. And in this case, they're all pretty consistent with each other. Choice subset 1 and 3 are very consistent with each other. Choice subset 2 is a little bit, it sneaks up a little bit. But one thing to keep in mind here is that there are different observations informing the three posteriors. So not only do we have different choice subsets, they're just different realizations of the data. So there's going to be stochastically different likelihood functions and slightly different posteriors. And so this is not unrealistic for consistent behavior when we're dealing with disparate data sets. And indeed, from our analytic construction of this model, we know that it should exhibit IIA. We know that there should be uniform substitution patterns. And so these choice probabilities should be fixed across all three choice subsets. And that would be consistent with what we're seeing here. So I know I said a little bit earlier, I was talking about choice subset 3 increasing more than choice subset 10. The choice probability for alternative 3 increasing more than the choice probability for alternative 10. Very much a mouthful. I'm jumping the gun a little bit there, right? There are uniform substitution patterns for this model from this data generating process. And so we should expect choice probabilities to be exactly the same. It's the same proportional increases or decreases everywhere. Ideally. And in this case, they're not exactly the same, and that's because of the disparity in the observations used in each of those posteriors. Now, the other thing that we can do here is instead of trying to fit each of those observations separately, we could fit them jointly. And if we have the right substitution patterns, then that joint fit should be just as good as the individual fits. In fact, it should be better, because we can now pool the information gained from all three data sets together into one consistent set of inferences. Just got hot water all over myself. And so the thing that we have to do here is we define single sets of a baseline alternatives, right? We're using the global indexing for our parameters. But when it comes to calculating the choice probabilities, we have to do that for every choice subset separately. And we have to make sure that we pick out the right local alternatives when calculating those choice probabilities. Right? And that's because the choice counts here, right? The meaning of the choice count, the index, the observed index within each of those choice subsets is different. So even though we're aggregating everything together here, we want to be a little bit careful because the meaning of those observations is different depending upon which segment of the array we're looking at. So it all like the critical thing here is just logistics, keeping track of what's what. Oh, yeah, and then the last thing that we can do here is we can make predictions for the log probabilities in any choice subset. Right? Assuming that our model is capturing the right substitution patterns, we can look at arbitrary changes to the alternatives and predict and make inferences for the choice behavior in those new choice subsets. And so here I'll choose just the full choice subset, which is technically just choice subset 3. But just for simplicity, we'll look at all of the alternatives. No computational problems when we run everything, and this is really key, right? If we have the wrong substitution patterns, and so we're using one model that doesn't really generalize, and we try to look at observations across that spectrum of generalizability, the likelihood function, the posterior we get, should be pretty awkward, right? You should get a lot of model contortion because it's not capturing the right behaviors. That can result in computational problems. It will definitely result in awkward inferential problems. So the fact that we don't see any computational problems is a good sign that we have the right substitution patterns. The restricted behavior looks good across all 3 choice subsets. Which lets us start thinking about choice probabilities. So we're looking at here. The advantage, again, to looking at a joint model, instead of just fitting everything separately and then trying to compare those posteriors, is we get smaller uncertainties by leveraging all of the information together. So if we look at our posterior inferences for omega 3 and omega 10, and behind in the lighter colors are from the separate fits, and then the dark red in front is from the joint fit. And you can see we are getting more information. We're getting smaller uncertainties for the alternative utilities, the alternative relative baseline utilities. And then so they're consistent with each other. They're just more informative. That means if we went back and looked at those racial choice probabilities, those substitution patterns, they would look exactly the same. So no kind of questions there. And then once we're confident that we've captured the substitution patterns correctly, we can then use that assumption, leverage that assumption to make predictions, make inferences about new choice subsets. Here we're looking at the choice probabilities in a choice subset, including all of the alternatives. Any questions about this independent Gumbel model, how we implement it, and how we might start looking at substitution patterns across multiple choice subsets, including fitting each of those choice subsets independently and then comparing inferences, or fitting everything jointly, and then looking at the inferences within the kind of generalizability assumed by that model. All right, so if there are no questions, and again, you can always ask questions later in the chat or on the Patreon, let's now move to more elaborate models. So if we're in a circumstance where independence from irrelevant alternatives is not appropriate, where these uniform substitutabilities is inappropriate, where we want some alternatives to be better substitutes for each other than others, we're going to move beyond the independent Gumbel model. Now, there are a few kind of classic generalizations of the independent Gumbel model that give us some very useful substitution patterns. They are quite exceptional in the sense that they allow analytic calculation, as we saw in the last live stream in the appendix here. Trying to generalize beyond the Gumbel to other extreme value models, immediately blocked by analytic tractability. However, it turns out there are some other ways of trying to bootstrap the independent Gumbel model to allow for more sophisticated behaviors without compromising on analytic tractability. There is another approach, which is more kind of approximate computation based, and we'll get to that in the next big section. So I would say from what I've seen, the main alternative to the independent Gumbel model is what's referred to as the nested Gumbel model. And the nested Gumbel model introduces a notion of nests. So nests are subsets of alternatives that are good substitutes for each other. So if I take two alternatives within the same nest, they're going to be good substitutes for each other, or they're going to be better substitutes for each other than any alternative in any other nest. So we can cluster the alternatives together based on what we think are good substitutes. And then use that nesting structure to get choice probabilities that respect that behavior. Now, it turns out the kind of way to navigate that is through this cumulative distribution function. There's a few ways of thinking about this, but it's often presented as, hey, here's an immediate mathematical generalization of the independent Gumbel model. If these lambda k's go to 1, then we recover the independent Gumbel model. But if these lambda k's are less than 1, then we get stronger coupling within a nest than across nests. So we can think of these lambda k parameters as a quantification of the coupling of the alternative baseline utilities within each of these nests. Or sorry, I should say the coupling of the alternative utilities within these nests. There's a few subtleties here. Technically, the lambda k's can sometimes be larger than 1. There are ways of tweaking the lambda k so that some of them are larger than 1, but they're kind of weird behaviors, and they kind of break a lot of the interpretability. So I'm just going to exclude those here and just focus on the more kind of well-behaved configurations between 0 and 1. And I think I mentioned this later, but I might as well mention it now. We can always just come back to it. The independent Gumbel model is often referred to in, especially the econometrics literature, a generalized extreme value model. Now, as far as I can tell, this use of generalized extreme value model is solely in the sense that if you take a discrete choice model based on this extreme Gumbel model, then you can generalize it into this nested Gumbel model. So it's a generalization of a discrete choice model using an extreme choice probabilistic utility model. Whereas in statistics, generalized extreme value corresponds to this joint family that covers all of the extreme value density functions together. That, again, we talked about last week is in the appendix. That statistical generalized extreme value model is not how you get to the nested Gumbel model. These are two distinct things. And it's very confusing. And so I could be wrong. I don't think there's a way of deriving the nested Gumbel model from a statistical extreme value perspective. And I think it's just a name that comes from generalizing this one exceptional extreme value behavior in the discrete choice context. But if I'm wrong, let me know. I'll be happy to resolve it. The one way I've found of trying to motivate a generalization of the nested Gumbel model is to think in terms of norms. So this is the cumulative distribution function for the independent Gumbel model, right? It's just a sum. It's an exponential of a sum of exponentials, where each exponential is this little kind of deviation term of the a particular baseline utility, sorry, a particular utility minus its baseline value divided by its scale, right? We kind of see this location scale quantity show up in a lot of density functions. Now, we can always, given a nesting structure, we can always split this sum into a sum over nests and a sum over the elements of the nests, right? But critically, we're not changing anything about how we calculate that inner sum. This is just a refactoring of the independent Gumbel model. That said, we now have an opportunity to think about this inner sum a little bit differently. In the kind of general theory of vector spaces, there's lots of different norms that you can use to quantify a notion of length of a vector, right? And if we think about a vector as a collection of components, then it's a way of kind of translating a set of component values into a single notion of magnitude. The sum of the component values is known as the one norm, sometimes known as the Manhattan norm, and there's all kinds of different terminologies for it. And that's what we have here. But we can always generalize this to arbitrary what are known as p norms. And in a p norm, you take each of those individual component values, you exponentiate it to p, and then you take the sum of those exponentiated components and you hit it with 1 over p, kind of undoing that exponentiation. Again, for p equals 1, we get the 1 norm, the same thing that we started with. If p equals 2, you get the 2 norm. This is your classic Euclidean norm where you square the components and then add them together and then take the square root. But we can take p to be any value, really. And if we allow p to be between 1 and infinity, then 1 over p is going to range between 0 and 1, and we recover that nested Gumbel model. So one way of thinking about the nested Gumbel model, or motivating its structure, is that instead of just adding up the elements in each nest with one norm, we add them up with a 1 over p norm, where p can vary across the nests, and then we add those nest contributions together. Why is this useful? Well, depending upon p, we get very different relationships between the individual component values and their sum. So in the 1 norm, the sum is kind of equally contributed to by each of these components. The only way for the overall contribution to be large is if all of those components are large. As p gets larger and lambda gets smaller, however, the overall sum, the overall norm, tends to be dominated by the largest values, which makes sense, right? When you exponentiate something to a positive exponent, you're amplifying the large values and suppressing the smaller values. And so when we take it to its limit, eventually, as p goes to infinity and lambda goes to 0, we're basically just picking out the maximum value in each of those nests. In other words, it doesn't matter what the individual utility behaviors are in each of for the alternatives within a nest. Their contribution of those elements is all the same because they've been warped through this very large p norm or small lambda 1 over lambda norm. And that's what gives us the coupling, right? They're contributing to the probabilistic utility model as if they were the same, even though they're not. Oh, that's another note there. Leo, you're asking here in the chat. I wish I get the coupling. Do you mean deriving, like calculating what the coupling is, or understanding the intuition behind the math here, or is there like a particular calculation or something that would be nice to have that we either you don't know how to do, or in general the field doesn't know how to do? I see. Um, so in Markov chain Monte Carlo theory, a lot of the results are based on things known as couplings. And so these kind of jokes are quite common. So they're at this point kind of old to me, just because I've had to deal with them for so long from the MCMC side of things. But yes, I recognize the appeal of a good joke about being sad and alone, as so many of us often are. All right, so we're talking about coupled utility models that generalize beyond the independent Gumbel model. So we have we can motivate this generalization of the independent Gumbel cumulative distribution function used in terms of these p norms. And again, it's just about a way of ensuring that the kind of contribution of each of these nest sums behaves as if each of the individual alternatives were behaving exactly the same, right? So the larger p is and the smaller lambda is, the more the sum behaves as if the u's were exactly the same, even if they're not. Now, the exceptional quality of this model is that it does admit explicit calculations. They're not necessarily straightforward. So I have done them, and I've done them out in full form in the appendix. But the kind of takeaway is you get choice probabilities that look something like this. Now, this might not look immediately all that nice, other than the fact that it is a closed form. But things become a lot cleaner if we do a little bit of a simplification here, or a little bit of factorization. So by just adding and multiplying some terms to the denominator and a denominator and numerator, we can factor the absolute choice probabilities into two terms. One is a conditional choice probability of choosing the jth alternative from the kth nest, right? So this is just like the independent Gumbel model. It's a softmax, the multi-logit function, or the logit function for short, over the relative baseline utilities divided by the agent scales, with an additional contribution from this lambda parameter. And again, the key thing is we're only summing over the nests, the alternatives within a nest. And then the second term, this doesn't depend on any particular alternative. It only depends on the nest that we choose. So what we've done is we've broken down the choice probability for any individual alternative into a conditional probability of choosing that alternative within a nest, and then a marginal probability for choosing that nest. And both the conditional probability and the marginal probability have these relatively nice forms. They both look like softmaxes. Indeed, they can be calculated with softmaxes. The conditional probabilities within a nest, that's just one softmax calculation. It's basically the same thing that we were doing before. The marginal probabilities require a little bit more work because we're not, we have these lambdas here. So we're not just summing, taking these kind of nest sums as the individual contributions. We're exponentiating them. So to get this into a softmax-like form, we've got to work with these quantities here. So for those who have not done a lot of mixture modeling before, you might not recognize this, but this is known as a log sum x function, where you take the input, you exponentiate it, sum them, then take the log. And so by putting that all together, what we get is something like this, where we log sum x over the alternatives in each nest. Then we scale those logsum x outputs by the individual nest parameters, and then plug that into a softmax. So the calculation of this stuff is pretty straightforward, right? Once you have a logsum x function and a softmax function, this is pretty straightforward to put together. I should note that these terms here, these kind of these nest logsum x functions, they do have. There's a lot of econometric discussion on these terms in particular as kind of quantifying useful information or summarizing useful information about the nests. I have yet to kind of find that as compelling as what I've read about. I think that once you're in a Bayesian context, you can look at any substitution pattern you want just by playing around with different generated quantities. These kind of things are less useful, but keep in mind that they are explicitly used in a lot of different analyses. And if you're in one of those analyses, no harm in saving these and keeping them around for summarizing to your colleagues or collaborators, putting in a paper, and so on. Like the independent Gumbel model, this nested Gumbel model has its redundancies. In fact, it kind of inherits the redundancies of the independent Gumbel model. So because you can write everything in terms of softmaxes, it's unsurprising there's going to be some translation redundancies kind of hiding around here. Now, it's a little bit more subtle in that these redundancies really only manifest in the conditional probabilities and not the marginal probabilities. So you might think that we have to, say, anchor an alternative in each of the nests separately or something like that. But it turns out we actually don't really have to do that. We can use exactly the same redundancy amelioration strategies that we used before, where we fix an anchor alternative, translate all of our baseline utilities into relative baseline utilities, and then construct relative scales, and so on. So basically everything that we did before in terms of the elimination of redundancies, the implementation of the model in terms of softmax, all of that carries over to the nested Gumbel model. It just requires a little bit more care in terms of the calculation. Any questions so far about the kind of basic mathematical structure of the nested Gumbel model? So Leo asking in the chat what the models are for. So this is our second live stream review of discrete choice modeling. So we captured in the first live stream, we kind of went over the basics of what a discrete choice model is, the kind of classic independent Gumbel model, the notion of substitution patterns within discrete choice, and so on. Today we're following along, getting into coupled utility models, the generalization, and the demonstration of the more sophisticated behaviors that these models can manifest. All right. So if we focus on ratios of choice probabilities, well, one nice thing about this model is that we can calculate a lot of those directly. So if we look at ratio to choice probabilities, we can think of this as the ratio of the conditional choice probabilities and the marginal choice probabilities. Right now we're going to get different behavior depending upon whether or not the alternatives are in the same nest. If two alternatives are in the same nest, then the ratio of marginal probabilities is going to cancel. And all that's left is the ratio of conditional probabilities. Now the ratio of conditional probabilities, because it reduces to this softmax-like form, well, all of the other contributions cancel, so we get to this difference of baseline utilities for the two active alternatives. This is exactly the form that we had in the independent Gumbel model, only it's isolated within a nest instead of the full choice set. In other words, the generalized, the nested Gumbel model doesn't completely eliminate independence from irrelevant alternatives. Instead, we get IIA within each nest. All of the alternatives within a nest are basically equivalent substitutions for each other. When we look across nests, however, well, now the marginal probabilities don't cancel. And now if we try to calculate things, we're left with contributions from all of the alternatives within the two nests that we're comparing. It's not all of the alternatives across the entire choice set. It's just all of the alternatives within the two nests that include the alternatives that we're comparing. And this is what breaks IIA more generally. So if we look at two alternatives and two different choice sets, if we remove a third alternative from one of those choice subsets, it's going to leach more probability from its neighboring alternative than its non-neighboring alternative. Similarly, if we add a new alternative to a nest, that's going to leach... Sorry, I got that wrong. Two alternatives. If you remove one alternative, there's going to be excess probability. It's more likely to go to the other alternatives in the same nest. If you add an alternative, it's going to need probability. It's going to prefer to take it from the other alternatives in that nest relative to alternatives that are not in that nest. Right? That's what gives us that more sophisticated substitution behavior. There's a coupling between choice probabilities within a nest more than there is across nests. And so I go through a little more you can try to make this a little bit more quantitative by looking at what happens depending upon the sizes here. But the main thing is that these sums over the nests, right? If you add an element, there's more things in that sum, it's going to get larger. If you remove an element, there's fewer things in the sum, it's going to get smaller. And so depending upon the value of lambda, that increase or decrease is going to transform the ratio of choice probabilities in a certain way. So this figure here just kind of emphasizes some of the kind of qualitative behaviors that we get. So if we have 9 alternatives split equally across 3 nests, what happens when we remove an alternative from the second nest? Well, all of the choice probabilities are going to increase at least a little, typically. But most of that choice probability that's freed up when we remove that alternative is going to go to the other 2 alternatives that were in the nest, that same nest. Right, so everything gets a little bit darker, but the 2 remaining alternatives in nest 2 get even more darker because there's more of an increased choice probability. Whereas if we add an alternative to nest 2, all of the choice probabilities will tend to decrease a little bit, but the choice probabilities of the existing alternatives in nest 2 will decrease more than the alternatives, right? So those will get lighter than what we see in nest 1 and nest 3. Right, and that's just this qualitative summary of what's happening when we're adding and removing nests and generalizing from one choice subset to another. We can also do some very long calculations, which again I have sequestered into the appendix. We can calculate the elasticities directly. And just from direct inspection, we can see that when we look at the differences of elasticities, they do not cancel in general. So if, and that's because there are these terms that are that come from kind of all the alternatives within the nest that alternative belongs to. So if we're looking at the 2 elasticities of 2 alternatives in the same nest, this extra term is the same. It does cancel, and we get to that kind of demonstration of IIA within a nest. But if we're comparing 2 alternatives across different nests, then these 2 sums, these 2 nest contributions don't cancel, and we break IIA, which is just a kind of in agreement with what we've seen so far. Whew. And then finally, I'm not going to go into these last 2 in too much detail, but you can generalize the nested Gumbel model even further by weakening the membership within nests. So instead of requiring that every alternative belongs in one and only one nest, more generally, we can allow each alternative to have some partial membership in each of the nests. And so we quantify that with these alpha parameters, which we can think about as, it's a simplex, right? So it's like the weight or the proportion of each nest that each alternative belongs to. So if these alpha these simplices kind of go into a one-hot configuration where only one of the alphas is 1 and the rest are 0, then that reduces to the nested Gumbel model. But this allows you to have just a little more flexibility in the nesting. It turns out that you can kind of continue the analytic tractability in this case. It is a mess. Again, I've sequestered all those calculations, so they're not super scary here. But you get choice probabilities that look like this. They can be reduced into conditional and marginal forms that aren't too bad, right? Despite the fact that the actual derivation of this stuff is pretty nasty, the final result isn't as scary as you might expect. And in the end, it's the same basic softmax and log sum exponential tools that you need over and over again in order to put all these things together. I won't be demonstrating this in the exercises, but it's here. So it's, you know, it's a nice example. If you want to kind of push these models even further, you can take what we've done in the nested Gumbel exercises and try them here as well. Although I will note, one thing I want to be really careful about is whether or not you're trying to infer these alphas or they're fixed. In most applications, these alphas are fixed. I haven't done too many experiments with this, but I'm pretty confident that the degeneracies for the alphas are going to be wild. Not that the model's redundant, it's just that it's going to be very, very hard to learn the consistent alpha configurations. It's likely to be like a clustering problem where there's going to be lots of different modes that are nearly equivalent with each other. And there's no amount of MCMC that's going to be able to quantify and find all those modes. And then the last generalization that we'll consider here is the probit model. The last coupled utility model. So this is taking a very different direction than the nested and generalized nested Gumbel models. So instead of working with a cumulative distribution function that has a nice clean form, we work just putting a normal on the probabilistic utilities. In theory, the calculation of choice probabilities is straightforward. It's still just the probability allocated to these particular subsets where one utility is larger than the others. The problem is that we cannot calculate those probabilities for multivariate normal and closed form. Right, these are very non-rectangular subsets, and there really just is no closed form of a multinormal probability. Another way of thinking about it is there isn't a closed form multinomial CDF. You can do multinomial CDFs in each direction independently, but there is no joint multinormal CDF that is available in closed form. So while this is, you know, everyone loves throwing normals on stuff, right? So why wouldn't this be a useful model? You can have all kinds of arbitrary couplings in the structure of the covariance matrix. Whether you learn them or you fix them, right? There's all kinds of nice flexibility and structure here. Well, the main problem with this model is, again, the lack of analytic tractability. We can't calculate choice probabilities. So the way this is typically handled in practice is the individual probabilistic utilities for each agent alternative combo are elevated to parameters. And then the observational model becomes discrete. If you happen to have a configuration where one of the U's is larger than the others, then the probability of choosing that particular alternative goes to 1, everything else goes to 0. This turns into discontinuous likelihood functions and discontinuous posterior distributions. Nothing theoretically wrong with this. It's just that those discontinuities obstruct the use of all of our state-of-the-art tools. You can't use any of the good optimizers. You can't use gradient-based MCMC samplers like Hamiltonian and Monte Carlo. So these kinds of models, the so-called probit model, has been implemented quite a lot in the literature using Gibbs samplers. So they're kind of very much given a Bayesian perspective. You build a big joint model with a discrete likelihood function or discrete posterior density function. You throw an MCMC that doesn't care about the discreteness, and you hope that it can explore all of the configurations of not just the probabilistic utilities, but the baseline utilities and this kind of baseline covariance, right? That's really what's interesting is learning these. Now, a few things. Note that this requires a lot of parameters, right? Every time you have a new agent, you have new probabilistic utility parameters that you have to introduce to your model. Every time there's a new alternative, you've got to add that to your model. And so when you're thinking about kind of the structure of mu and sigma, it has to cover all of the possible alternatives, and then you can subset it for any individual choice subset. Oops. Ooh. Don't want that. So in general, you're adding lots of parameters, and you're getting these big high-dimensional models, which in general isn't a problem unless you're using something like a Gibbs sampler, which is not very good at trying to explore high-dimensional distributions. So it's one of these unfortunate circumstances where Gibbs sampling is kind of the only tool you can use, but Gibbs sampling is also just really bad at diagnosing its own inadequacies. And so it might look like things are well behaved, but you're very often missing huge swaths of uncertainty. And because you can't apply something like HMC to these models, you can't see what you are missing. So in general, I'm not a fan of these approaches because we can't use our really robust tooling on them. And it's very difficult to have conversations about the limitations of these models because it's hard to demonstrate just how bad they are empirically beyond, say, just pure simulation studies. So I won't be talking about them any further. All right, before getting into the exercises, any questions about the implementation of the independent couple model or the mathematical structure of any of these coupled utility models that we've discussed so far? All right. So, exercises. This is going to follow in a very similar progression to what we did before. We're going to simulate some data for a single choice subset. We're going to see what happens when we try to fit data to it. And then we'll look at multiple choice subsets and see if we can infer substitution patterns. So we'll have 3 nests here. I will just fix the nesting configuration. This is not something we model. We decide which alternatives belong to which nest. And then we have these coupling parameters within the nests that we can either infer or fix. You'll see a lot of applications where they get fixed, which is always going to be a tricky thing when you don't actually know it that confidently, but often has to be done for computational reasons, as we'll see in a little bit. And then we can simulate from the model. Now it's a little bit more complicated because we have to deal with the sum over nests and then the alternatives within each nest. But with a little bit of care, it's not that tricky. We get these marginal probabilities within the nests, and then we can calculate the contributions within each nest and put all of that together to compute our overall log probabilities. Once you have the log probabilities, everything's the same as it was before. You pick an agent, you pick a choice from the log probabilities for that agent. So simulating things is not a problem, and then we can aggregate our choice counts and use the multinomial model like we did before. So we have our histograms to visualize the aggregate choice counts. Again, it's a single choice subset, so we can look at everything all together. We can stratify. In this case, we can not only stratify across agents, we can also stratify across nests. And so this kind of gives us a sense of the conditional frequencies of choices within each of the nests. And then we can also look at the frequency of the nests themselves. So how often is an alternative chosen in the third nest? Right? So if you look up here, alternative 2 is chosen a lot within the first nest. But overall, it's not chosen that often because nest 1 isn't chosen all that often. Right? So it's both the conditional and the marginal behavior that we have to consider together. So the first thing we're going to do here is, instead of trying to model, so we know that we're simulating data from this more sophisticated coupled utility model. But what happens if we just take our naive independent Gumbel model? Well, oddly, there's no computational issues. And if we look at a retrodictive comparison, it looks great. That's weird. In fact, if we look at our inferred choice probabilities, they're quite good. The only thing that's a little bit weird is that the inferred baseline utilities are off. So this is a nice demonstration of the fact that the independent Gumbel model can do arbitrarily well for a single choice subset. If you only ever have one choice subset, there are no other choice subsets to consider. There's really no relevance for substitution patterns. And so the fact that our independent Gumbel model doesn't capture the right substitution patterns doesn't matter, because we're not looking at substitution patterns here. The independent Gumbel model will always be able to fit the behavior within a single choice set. It's not going to get the parameters right necessarily, but that doesn't matter, because those parameters are more important to the substitution behavior than anything else. All that matters within this choice set are the log probabilities, and the independent Gumbel model is getting that no problem at all. Right, so this is a very, very important thing to keep in mind. All of these generalizations beyond the independent Gumbel model really only matter when you're looking at actual substitution patterns. When you're either trying to aggregate data across multiple choice sets, you're trying to make predictions in new choice sets, and so on. That said, we should be able to also get good behavior within this one choice subset using the nested Gumbel model that corresponds to the actual data gen process that we simulated from. So let's see if we can do that. So one thing that I've added here are these num which int and which int functions. These aren't strictly necessary, but what they allow us to do is take a particular alternative and calculate which nest it belongs to. So you could just code that in and have, an additional array that you pass in as data that allows you to map back and forth between alternatives and nests. Here, we can just calculate it on the fly, and that just makes the code the model overall look a little bit more simple. Right, so I can grab which alternatives are within each nest, and instead of having to pass that in with another ragged array structure. So not strictly necessary, but I do think it makes the programs a little more elegant. Now, this is the correct model, right? But we're now getting computational problems, which is frustrating. So we get computational problems, we see divergences. We want to start investigating them and see what's going on. So first, before kind of looking blindly at pairs plots, we want to think a little more carefully. Which pairs plots are likely to be the most informative? Where might we see degenerate behavior? Well, if we examine the structure of the nested Gumbel model, we're getting a lot of terms like this, right? A lot of the contributions to the choice probabilities are of the form of a relative baseline utility divided by a relative scale divided by this nest scale, this nest coupling parameter. And so one thing that we can see is that when we look kind of independent of agent, we're just looking at a single alternative. It's always going to be the same ratio here, omega to lambda, right? Lambda is always the same when we pair with a particular omega, because each alternative is always in the same nest. And so the data is really mostly going to inform this ratio here, rather than omega and lambda separately, or it's potential that there could be a degeneracy with regard to that ratio. And so let's look at omega versus lambda. And indeed, if we look at across our nest, we can see that there is this kind of pinching behavior as we get down to smaller and smaller lambdas. Here's our anchor, right? That one's a little more exceptional. But you can see that the green are starting to get more and more concentrated as we get this tightening, where we go to larger omega and smaller lambda. So this suggests that maybe these divergences are indicating that our exploration is getting obstructed by the geometry exhibited by this kind of redundancy between omega and lambda. So one way of trying to avoid that is by parameterizing our model not in terms of the ratio, but in terms of zeta. So we parameterize that ratio directly, and then model zeta and lambda. We can always then recover omega from that, right? I can always go from omega and lambda to zeta. We can also go from zeta and lambda to omega. The only problem with this is that the zeta will have a very different prior model than the omega. Now, I don't want to try to derive what that might be, but we'll just do a little back of the envelope here, just to kind of get 99% of the way there. The dark red here are the Monte Carlo simulations of what the prior behavior for zeta should be. And the light red, we have a Cauchy approximation. So you can see that it's not quite right. The Cauchy is kind of a little bit too peaked in the middle, where the true behavior is a little more rounded. And then the true behavior, look a little more carefully, it's more rounded, it has more of a shoulder, and then it actually does have heavier tails as you go further out. You can derive this analytically. It's a mess. We're just going to use this Cauchy approximation to it. In terms of kind of domain expertise elicitation, it's not like we really elicited our domain expertise much more precise than this anyways. So we can put all this together, and we get more warnings, but they're less problematic warnings. So we're getting a few maximum tree depth. That's not a terminal failure by any means. And then we have some effective sample size warnings. Now, these are weak warnings. They're very close to the threshold. None of this would be, the sampler's working really hard. It's likely that there's a very extended posterior, but it doesn't mean that we can't trust the posterior computation. And so if we go back and look at the pairs plots for what we were looking at before, we can see that indeed, the light red is what we had before, the dark red is what we have now. We're exploring much smaller values of lambda than we had before. Right? So we were getting obstructed. And the free parameterization helps us get around that a little bit. So as more trustworthy computation, we can now look at our inferences, and indeed we see that our inferred choice probabilities, our retrodictive behavior is great. The inferred, both kind of across each individual alternative, across the nests. The inferred choice probabilities match with the true behavior, and now our utilities and scales match the true behavior. You'll note there's a lot of uncertainty here, and that's because of the uncertainty in lambda. So if you look at our inferences for lambda, you can see that there's some constraint, but not much. And all of this has a really important lesson, right? The lambdas determine the coupling within the nests. And the coupling within the nests only really manifests when we look at substitution patterns, when we look at data across different choice subsets. Here, we only have data for a single choice subset. All of this extra flexibility of the nested Gumbel model is irrelevant to trying to fit or infer the behavior in this one choice subset. So in other words, there's really not much we can learn about the lambdas. And if we can't really learn much about the lambdas, we're not going to learn much about the omegas. So if you only ever have one choice set, and you're never going to deviate from that one choice set, you might as well just use an independent Gumbel model. Yes, you can use more sophisticated models, but you can't learn all of that new sophisticated behavior. And so it's just going to be a more difficult model to implement, and it's going to be a much more difficult model to fit. Any questions about the behavior of the nested Gumbel model when working just with this data from a single choice set? All right. So what really matters here are multiple choice sets, right? This is where something like the nested gum model can become really useful. So to set that up, we're going to use the same alternative setup that we had before. So 9 alternatives, 3 nests, and the same nest couplings. But now instead of having one choice subset, we're going to have 9 choice subsets. Now I'm going to randomly sample 7 of those choice subsets. So the size, the number of alternatives is going to be random, and then the actual alternatives that are chosen, that are included, are going to be random. 2 of them I'm going to fix. And this is so that we have the same kind of... we can examine the same substitution pattern that we did previously. Or a similar substitution pattern. So choice subset 8 is missing alternatives 5 and 9. Choice subset 9 is missing only alternative 9. So we can get from 8 to 9 by adding the 5th alternative. We can go from 9 to 8 by removing the 5th alternative. When we add the 5th alternative, right, that's going to leech probability from other alternatives that are in that same nest. So up here we can see that the 5th alternative is in nest 2. So it's likely to leech probability from alternatives 4, 6, and 7, much more than from 1, 2, 3, or 7, 8, 9. So we're going to compare are alternatives 4, 7, and 2. Alternatives 4 and 7 are in nest 2. So they should get affected strongly when we add the 5th alternative. Alternative 2 is not in nest 2. It's in nest 1. So that should be relatively unaffected when we mess around with the alternatives in nest 2. Oh, look, and yeah, we can calculate that directly and see that the first 2 are nest 2. The last is in nest 3. And so consequently, the ratio of QJ1 to QJ2, right, that should be consistent across choice subset 8 and 9 because we get IA within the nest. Okay, here's another error. So that second one should be a... It should be QJ1 over QJ3, not QJ2. This ratio will change. Either because QJ1 decreases faster than QJ3, or QJ1 increases faster than QJ3. Or vice versa. Alright, so with all that said, we can now simulate our data. And now we have to consider not just what the agent is, but also what subset we're in. So once we have our choice probabilities, it's just a question of sampling an agent, sampling a subset, and then picking out the right choice probabilities, simulating a choice. And just for comparison's sake, we're going to make predictions about choice probabilities for the full choice set for the 5th agent. We can calculate those just to have them on hand, right? So kind of the true choice probabilities across the full choice subset. So lots of possibilities here in terms of data exploration. We can look at all of the aggregate choice probabilities using their global indices. We can look at the behavior within, we can use the choice in nests. We can look at the behavior within the nest. We can look at behavior across the choice subsets and so on, right? So lots of different stratification possibilities here. All of which could be manifesting very complicated substitution patterns. So when we're working with just that one choice subset, the independent Gump model worked fine. Is that going to carry over here? We're now working at multiple choice subsets. Well, let's give it a try. So we figure out a consistent anchor. We fit our independent model for each of those choice subsets like we did before. Each of them all look fine, which makes sense because each of them are just fitting one subset of data. So each of these separate models is able to fit each choice subset independently and adequately. However, if we start trying to compare inferential behavior, we start getting very different results. So not only do the inferred, say, relative baseline utilities not agree with the true behavior in some cases, they largely don't agree with each other. Right? So some of this can be attributed to the fact that each of these fits is using different data. But some of these are much larger deviations than we had before, right? Especially if you start like kind of pinning out the most extreme. There's not a lot of overlap between the kind of the posterior for omega 4 that concentrates the largest values and those that concentrates on the smallest values. And so this is what happens when you have non-trivial substitution patterns and you try to fit these separate independent Gumbel models. Like, each of them will fit separately just fine. But those inferences won't agree with each other. They don't generalize the way we would want. Now, we can try to force consistency by fitting everything jointly. But in this case, we now start getting bad retrodictive behavior across all of those choice subsets. It's the actual magnitude of this agreement is, a little bit heterogeneous, but overall none of these fit super well. Maybe choice subset 5, you could kind of, squint and say that's okay, but in all of the others there's at least one that deviates pretty strongly. And so what's happening here is we have all of these choice subsets. And in order for the model to kind of capture all of those different observations consistently, it needs to be sufficiently flexible to capture the right substitution patterns. The independent Gumbel model is not sufficiently flexible, so it kind of contorts itself to try to fit everything. And not only is that going to do a poor job of fitting all of those in separate behaviors across the different choice subsets, but it's also going to generalize poorly to other new choice subsets that we might consider in the future. And this is typically how a model that's too simple is going to fail in this discrete choice setting. It's going to fail when you look at observations across multiple choice subsets where you really start being sensitive to the substitution patterns. At the same time, if you have data across multiple choice subsets, then you can learn those substitution patterns with a more sophisticated model. And that's hopefully what our nested Gumbel model will allow us to do. So again, we're fitting all the data jointly, being careful to pick out the right choice probabilities for each choice subset, but those choice probabilities are being calculated from this nested Gumbel model. No computational problems, and our retrodictive behavior is much, much better than it was before. Right? We get really nice agreement across all of the choice subsets. We could also look at this more carefully. We could look at this in aggregate. We could look at this across nests and so on to dig into that even further. Now our parameters are consistent with the true behavior, both the scale and the baseline utility. And scales in particular got pinned down quite well. And we can learn the lambdas. Right? So before, with just that one choice subset, we had very little information constraining the lambdas, the coupling, the nest couplings. Now, however, we have that information. So not only can we learn omega and tau, we can also learn those lambdas, which is why we don't have to use that zeta parameterization here. So now let's look at substitution patterns. So we have agent 5, and we have our 3 alternatives. Alternative 4, 7, and 2. Remember, 4 and 7 are in the same nest, so those should be coupled together with other alternatives in that nest. And then alternative 2 is kind of separate. And so if we kind of play around with nest 2, we don't expect the probability of alternative 2 to change all that much. So we go from the... so choice subset 8. Remember, that was kind of our fixed baseline choice subset. And we go to choice subset 9. Choice subset 9 introduces a new alternative into nest 5. Sorry, into nest 2. Alternatives 4 and 7 are also in nest 2. So what's likely to happen to those? Well, we need choice probability for this new alternative. It's going to be preferentially taken from the other alternatives in that nest. That includes 4 and 7. So we should expect that the choice probabilities for 4 and 7 decrease more than the choice probability for 2 does. And indeed, that's exactly what we see. So there's a small decrease in the choice probability for alternative 2. But there are large decreases in the choice probability for 7 and 4. Sorry, these are log probabilities here. I should also be more careful about this. So here we're looking at the... I'll write that down. Everything's so complicated. Okay. And then we can formalize this in the ratios as well. So if we look at right, the ratio of J4 to J7, whether we're looking at choice subset 8 or 9, it's the same ratio, right? Because these exhibit independence from relevant alternatives. Looking at the ratio of choice probability for J1 over J3, however, we see a big difference. So we're seeing exactly the manifestation of the substitution patterns that we derived mathematically before. But now it's a little bit more explicit. We can play around with it and look at any different kind of agent or alternative combo that we might consider. But it really comes down to intuitively, again, what are those substitutabilities? How much does one alternative look like another alternative in the context of the choice that's being made? Two alternatives that are very similar to each other, or a collection of alternatives that are very similar to each other. If you add another one that's also similar, then the kind of couple choice probabilities will have to go down. Or the substitutable choice probabilities will have to go down. Whereas two alternatives that aren't good substitutes for each other, they're going to be less affected when you add substitutions for other alternatives, right? And the nested gumball model is just one way of quantifying that. Is by clustering all the alternatives into nests, and then saying that the alternatives within each nest are good substitutes for each other. The alternatives across nests are less good substitutes for each other. The generalized nested gumball model takes that even further by allowing you to have this kind of partial membership in each of the nests, so that which allows you to have even kind of more subtle and sophisticated substitution patterns, where there's even more of a continuous notion of substitutability rather than the 0-1 membership of nests. Any questions about all of this so far? So I'm a little, while people have a chance to think about questions, I'm going to ponder what we do now. So there's 2 sections left. Section 6 is pretty straightforward, but it has 2 long exercises. Section 5 is long. And so I'm a little bit hesitant. We're kind of at a natural stopping point, both in terms of time and material. But I'm a little bit worried about trying to save both sections 5 and 6 for next week, because that'll probably become a really long one. So I think what I'm going to do is try to take 15, 30 minutes maybe, and just start section 5. Just try to get some of that out of the way so that next week won't be quite as bad. If anyone has to leave or sneak out, no worries. Of course, this is always going to be recorded, so you can come back and check it any time at your own convenience. So let's go a little bit further and start digging into mixed discrete choice models. So from what I understand of my kind of collaboration in applications that use these kind of models and working through the literature, the nested gamma model, as nice it is, isn't all that common. The majority of discrete choice applications introduce more sophisticated substitution patterns in a different way. Instead of trying to come up with an entirely new behavioral model that generalizes the independent gamma model and then working through the nasty calculations, what we said to is start with the independent gamma model and then convolve it with another model. In other words, we'll take a base utility model, which might be the independent gamma model that we used initially, and we introduce a mixture kernel. And we derive a continuous mixture model. We can derive a new behavior model as a continuous mixture of the base model and this mixture kernel. And this mixing, depending upon how we do it, can introduce more sophisticated substitution patterns than existed in the base utility model. Right? There's a few ways of thinking about this. Perhaps the most useful intuitively is that if the substitution patterns for the base model vary with phi, so maybe for a particular phi, the substitution patterns are very simple, but for different phi, we get different substitution patterns. This continuous mixture model is going to combine all of those different behaviors together at once, and that can give us a model with more sophisticated behaviors. Now, if we assume that our base mixture model is sufficiently well behaved, so it's continuous, there's no kind of weird, discontinuities or kind of stuff that messes up limits, then this continuous mixture where we integrate over this mixture kernel, that just commutes with all the other calculations that we've done. And that means that we can always think about deriving a new behavior model. We can also just think about deriving a new cumulative distribution function as a continuous mixture of a base cumulative distribution function. And then as we kind of go through the calculations of the actual choice probabilities, the same commutation happens. And we can just wait and do this mixture over the mixture kernel last. Or we can do it at any stage we want. And that will allow us to implement these models, not through analytic calculation, but by the introduction of a larger joint model and a more expensive computational problem. Now, formally, this is a continuous mixture, which I talk about in the mixture modeling chapter. But these models are oftentimes just referred to as mixed models. And it's not really telling you what you're mixing or how you're mixing it. It's kind of taking some of the assumptions for granted. Not uncommon in a lot of terminology. But the most common term for this is a mixed model. In marketing in particular, you'll hear marketing mixed model thrown around, or MMM. I think this is one of those terms that's fun to say, probably why it's so common. But anytime you see MMM, mixed model, mixed marketing model, marketing mixed model, they're all just referring to these kind of continuous mixtures. So the utility of a mixed model depends on, you can't just say that a mixed model is good or bad. The utility of a mixed model is going to depend on the structure of the base utility model and then how you mix it. A lot of the utility, a lot of the gain that you can get by going to a mixed model is in how you engineer this mixture kernel. how you engineer this mixture kernel will then determine how hard this model will be to implement. So there's going to be a lot of challenges in how we engineer this, and then how we derive these marginal choice probabilities. So as I mentioned before, the nice thing about a continuous mixture model in the context of discrete choice modeling is that all of our calculations are integrals and derivatives. And provided that the base utility model is sufficiently well behaved, which it will be for anything that you might write down by hand, then we can exchange all of these integrals and derivatives, which means that we can, instead of doing the continuous mixture first, and then deriving a CDF, and then deriving choice probabilities, we can also derive all choice probabilities first, and then mix them. So we can write our model in terms of a mixed CDF. We can have mixed derivatives of that CDF, and then that will eventually lead to these mixed choice probabilities. I'm going to refer to the mixed choice probabilities as marginal choice probabilities because they are marginal from this continuous mixture. Whereas I'll refer to the initial choice probabilities as the base choice probabilities. Just it's not really standard terminology in it by any means, but it's something that will help us kind of differentiate the two at all times instead of just relying on the parameter argument alone. So if we were to start with the simplest discrete choice model as our base, the independent Gumbel model, we have those explicit choice probabilities. So instead of having to take the independent Gumbel model, mix that, and then rederive a CDF and choice probabilities, we can also just try to mix over the choice probabilities directly. And then we have a lot of options, right? Because we have our baseline utilities, we have our scales. We can mix over those. We can mix over relative baseline utilities, relative scales. We could derive the baseline utilities from functions and then mix over the parameters of those functions. All kinds of possibilities here. But most often what you'll see when using the independent Gumbel model as a base is a mixture kernel over the baseline utilities. And indeed, we'll spend a lot of time talking about that. So what's so special about mixing an independent Gumbel model? Well, there's a few ways of thinking about it. We'll get to the general intuition in a little bit, but the first thing that we'll see is that just introducing an integral in the choice probabilities blocks a lot of calculations. It blocks a lot of cancellations. And that forces more sophisticated substitution patterns. So let's assume a base independent Gumbel model. Let's assume that we're mixing over the baseline utilities. And just to clean up the notation a bit, we'll use this kind of vector notation for the baseline utilities and their differentials. This is also referred to as a random utility model, especially in the economics literature. Although it is somewhat weird because it's what's random here, what's probabilistic are the baseline utilities, not the utilities. Right? This is back to what we were talking about last week in the first review, where there's a lot of sloppiness in terms of things like the probabilistic utilities, the baseline utilities, and so on, right? Those kind of just get convolved a lot and kind of confounded for each other. So as the classic example of this is in the independent Gumbel model, if we look at the ratio of two choice probabilities, the normalizations always cancel identically. And what we're left with is the exponential of just the two choice probabilities in this ratio. But if we try to do this with mixed independent Gumbel choice probabilities, well, we have those common normalizations, right? It's the same normalization in the numerator and the denominator, but now we can't cancel them because they're inside of an integral. We can't factor those out of the integral because they depend on the baseline utilities that we're mixing over. So consequently, we don't get a nice simple form like this. The ratio of choice probabilities in a mixed independent Gumbel model will, in general, aside from kind of trivial cases where the integral doesn't do anything, not give you a function of just mu j1 and mu j2. And so we no longer have independence from relevant alternatives, because the normalization, the contribution, the behavior of all the other alternatives in the choice set changes the integral, or changes the function we're integrating, which then changes the ratio. Similar thing happens when we talk about elasticities. When we're looking at elasticity, the integral pops in and prevents us from pulling certain terms out that would then cancel to give us these nice clean forms. So the cancellations of the independent Gumbel model are quite fragile, in the sense that anytime you introduce just a little bit of an integral, a little bit of a mixture, they no longer cancel perfectly, and we get deviations away from that very clean, simple, independent from relevant alternatives behavior. And just going through some of the basic results there. Now, that showing that you've violated independence from relevant alternatives, that you no longer have that one extremely rigid and simple substitution pattern, isn't super compelling, right? Because it doesn't tell you what substitution patterns you do have. Now, the general intuition seems to be that when you're mixing over baseline utilities, the more coupled two baseline utilities are, the better substitutes they'll be for each other. So if you remove one alternative whose baseline utility is strongly coupled with the baseline utility of another alternative, then the probability that was initially allocated to that first alternative is more likely to go to that second alternative than any of the others whose baseline utilities are less coupled with the eliminated baseline utility. So this is not a very good calculation, I will straight up admit, but it's my best attempt to get like a rough sense as to like why. Where you can kind of look at the choice probability calculations in two choice subsets where one of the alternatives has been removed. And you get terms like this. And the basic idea is that you, if mu j1 and mu j2 are very tightly coupled with each other, then this term stays very close to 1. Whereas if they're not very coupled with each other, you get a lot of kind of oscillations that all tend to cancel out, and you get a smaller contribution overall. This is not very compelling mathematically, and I think this is something the last thing I would really want to add to this chapter is a better understanding of this intuitive notion of coupled utilities or coupled baseline utilities leads to better substitutes or more strong substitutes. And I've seen this repeated over and over again. It's kind of taken for granted, but I've yet to see it kind of demonstrated from a very quantitative perspective. And I can't figure out how to do it. So if anyone knows any literature or any references that kind of approaches this or has an idea of how to calculate it, I would love to hear about it. So definitely let me know. But the kind of takeaway to all of this is that instead of just trying to violate the substitution patterns of the base model, in particular trying to violate independence from irrelevant alternatives from a base independent Gumbel model, we can think a little bit more productively, a little more proactively in what kind of couplings we want there to be between the baseline utilities in our mixture. Which baseline utilities should be more tightly coupled in the mixture than others? Or how can we allow there to be arbitrary couplings between arbitrary baseline utilities? And that leads us into the multivariate normal baseline mixing kernel model, which has no end of different names for it. But from what I've seen, it tends to be the most common discrete choice model in practice, where you take a baseline independent Gumbel model, and then you assume a mixture kernel over the baseline utilities that's multivariate normal. And then the structure of the location parameters and the covariance matrix of that mixing kernel is what gives you very particular substitution patterns. And so by constraining sigma, you can enforce certain substitution patterns. By learning sigma, you can learn all kinds of various substitution patterns. That said, while this seems pretty straightforward mathematically, there's a lot of mess that comes out of this. So what we'll talk about starting next week is the kind of general construction of this model, some of the particular special cases that are kind of well-known models in of themselves, or approximate models that we've already talked about. Then we'll talk about the redundancies of this model, which is kind of a mess. How it can ameliorate, or kind of identify and then ameliorate those redundancies in practice, which is just a much harder problem than it was before, because the redundancies are not just in the mu's. The redundancies are in the kappas and the sigmas. And so a lot of weird things can happen if we're not careful. Fortunately, we can use a lot of linear algebra to make this a very systematic procedural approach. Then we'll put it all together into some a practical implementation where we don't actually marginalize over the mixture parameters. Rather, we build a joint model, as we do, for example, with hierarchical modeling, and then we'll demonstrate all of this. After that, we'll talk about derived based on utility models, where we don't model the mu's directly. We derive them from a function. And this gets into things like factor discrete choice models, regression discrete choice models, and so on. So it kind of puts all those bits together. I'll give one last chance for questions here for any stragglers who are still around. As always, if you're watching this in the future and you have questions that pop up, or you have any recommendations about some of the kind of inadequacies that I've been discussing, please feel free to comment on the Livestream page directly. You're also welcome to comment on the chapter release page. And you can always just message me directly on Patreon if that's easier. All right, if there are no questions remaining, thanks to everyone who attended live. Thanks for all the chatter in the chat. It's always nice to see not only questions, but people kind of chatting back and forth. Thanks for the support, and we'll see everyone next week. Cheers.